As the question says, suppose in certain conditions only those transitions are allowed to hydrogen atoms in which the principal quantum number n changes by 2. Then find the smallest wavelength emitted by hydrogen and list the wavelengths emitted by hydrogen in the visible range. Now, if this is the smallest wavelength, then we need to find the maximum energy. And we all know, if this being the first, second, third energy states and so on, then the maximum energy transition takes place from 1 to infinity. But n change is allowed only by 2 units. This means that the maximum energy change here can be from 1 to 3. Getting my point? So that is the same thing. We are having n1 to be 1 and n2 to be 3. And so the energy is equals to 13.6 z square by n square, z square being 1 and n square is 1 by n1 square minus 1 by n2 square equivalent to this. And it is further equals to hc by lambda. Now friends, most of the times I see people getting confused in which one is n1 and which one is n2. You just don't care about that, because in any way you need this wavelength to be positive. In case it comes out to be negative, then there must have been your initial assumption of being positive or photon emitted or absorbed. Means if you have some criteria, suppose positive is indicating photon absorbed and negative being photon released and lambda is coming negative, it means that the photon is released. So simply you just don't care about the negative sign, you just make this bracket to be positive anyhow. Because 1 by 4 minus 1 by 9 is automatically going to be positive. But if it would have been 1 by 9 minus 1 by 4, then it would have been negative. The same magnitude with a negative sign. So it doesn't matter. You just have to make it positive and then equate it with hc by lambda, because lambda needs to be positive. So this gives us the value of wavelength to be 103 nanometers. So this is basically the smallest wavelength emitted by the hydrogen if this restriction is put up. Now proceeding to the second part, in which we need to find the wavelengths in visible range. Now friends, we consider the case of 1 and 3. It is 103 less than 380. Then the other 2 unit change can be 2 to 4 or 3 to 5, 4 to 6. So if we look at the transition from 2 to 4, we have the energy to be 13.6 into 1 by 4 minus 1 by 16, and equating that with hc by lambda, we get lambda to be 487 nanometers, which lies in the visible range. Now if we calculate the wavelength of 3 to 5 transition, you will observe that that comes to be greater than 780. So only this wavelength comes out to be in the visible range.